Hello again. We are covering transformations of functions in this video. We've covered this topic before, so we are just going to emphasize it here. So take notes and make sure you message me as you're watching the videos if you have any questions. Okay, so 2.6, transformations of functions. So this is where we do the shifting. So we've done shifting, shift up, shift down, shift left, shift right, multiply the original y values, reflect it. So we're doing that again, but that's all we're doing in this section. We're not combining it with other topics. So transformations of functions. Okay, so generally you're given a parent function. And we looked at some parent functions earlier in, I think, chapter P. Maybe it was chapter 1. So you're given a parent function f of x. Okay, and so we have these different transformations. We have the vertical shift. And this here happens when you take your parent function and you add a constant to it, or you have your parent function and you subtract a constant from it. So like maybe you have some parent function and you add 3. Okay, so if you add this constant to it, then it shifts your function up c units. If you subtract c, then it shifts your graph or your function down c units. Okay, so for example here, if you have this function x squared, right? That's your parent function, x squared, and you add 3 units to it, this would shift up. Okay. Here, let's write down what the parent function is. So if you have this parent function, f of x, which is x squared, okay, that's your parent function. So if you do x squared plus 3, this would shift your parent function 3 units up. If you subtract 3, this would shift your parent function down 3 units. Okay. And it doesn't necessarily have to be the x squared function. It could be the square root function. It could be the absolute value function, whatever the parent function is. This this operation here causes this vertical shift. Okay, so let's take a look at the horizontal shift. The vertical shift is intuitive. This one, I think, is not as intuitive. Let's have a look. So if you're given a parent function, so if you're given a parent function and you add or subtract c from that parent function, you get that vertical shift. However, if you add or subtract c from the x value, then here you have, if you add c to the x value, then this is actually a left shift. And if you subtract c, this is actually a right shift. Okay, so if I have, for example, suppose that I have this parent function. I'll use a different one from x squared, but you could use it for x squared, any of these parent functions. Okay, so suppose that your parent function is the square root function. Okay, so what happens is if you add c to the x value, then what happens here is you have to shift this. Here, let's put an actual number. Let's put x plus 3. Okay, so here, if you add 3 units to the x value, then you will shift left 3. And if you subtract 3 from the x value, then we will shift right 3. Okay, so make sure you can tell the difference between the vertical shift and the horizontal shift. And make sure you understand that plus 3 here is vertical up 3 units, negative 3 is down. But over here, plus 3 is to the left and minus 3 is to the right. Okay, so let's take a look at graphing, just doing these vertical and horizontal shifts. So let's look at this example. Okay, so graphing. Let's take a look at this example. Graph g of x, which equals absolute value x plus 2 minus 1. Okay, so here we're adding 2 to the x. So we know that this here is going to cause a horizontal shift, and it's going to cause a shift to the left. And this will be down. Okay. Okay, so we know the parent function is this one here, absolute value x, okay, which is that v function, right? Okay, so let's go ahead and graph this, the parent function. Okay, and we know that that's the v-shaped. It looks like this, okay? And I'm just going to do a dashed line. I'll do a solid line for my final. Okay, so this is the parent function. This is what the graph looks like for absolute value of just x. But now we want to graph not just absolute value of x, but we want to graph absolute value of x plus 2 and then minus 1. Okay, so this is very easy to do without a table of values because we can just take the parent function, which is this dashed graph right over here, and shift it 2 units to the left and 1 unit down. Okay, so left 2. All right, so left. So all of these points, 1, 2, 3, I have 3 reference points, but all of the points of this graph will shift left 2 and down 1. Okay, so I'm going to take this one over here and shift it left 2, 1, 2, and down 1. Same thing with this one. I'm going to take this point right over here and shift it left 2, 1, 2, and down 1. And same thing with this third point over here. I'm going to take this third point over here and shift it left 2, 1, 2, and down 1. Okay, and there is my final graph. Okay. Okay. Let's go ahead and take a look at reflecting graphs. So reflecting graphs, so kind of flipping them over the x-axis or flipping them over the y-axis. Okay, so if I have my parent function, okay, and I multiply that parent function by a negative number, okay, then what happens is it reflects this parent function over the x-axis. And we've seen that before where we have the parabola. We may have started like this, then we multiplied by a negative, and then it flipped it over like that, right? Okay. All right, so that's what we mean by reflecting over the x-axis, okay? If I take the x value and multiply it by a negative, then this reflects it over the y-axis. Okay, so let's take a look at a few examples. So let's take a look at this. Suppose that I have my parent function. And we're going to go ahead and use f of x equals square root x because you can see the reflection for both of these cases clearly. Okay. And if you remember, the parent function looks like this. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. So this is what the parent function looks like. It's really like a sideways parabola, but only the top half. So it's kind of like that, but only the top half. Okay. All right. So let's go ahead and let's suppose that I have this one. G of x equals negative square root of x. So that's where we multiply the parent function by a negative number. And then over here, we'll take a look at what happens when we multiply the x by a negative. Okay, so here we said that multiplying the parent function by negative reflects it over the x-axis, whereas multiplying the x by a negative reflects it over the y-axis. Okay, so here when we graph, so here I'll go ahead and put the parent function. Here is the parent function, and I'll do a dashed graph. Okay. And then here, we are multiplying the parent function by negative, so it will reflect it over the x-axis. Okay, so we have a point here, and then a point here, and then a point. This one gets reflected down here. Okay, so our final graph is this solid curve down here. Okay. Again, that dashed one is just the parent function. Okay, so that your final graph will just be this piece here on the bottom. Okay. All right, let's take a look at this one. So let me put the parent graph. Okay, so here is the parent graph, right? And multiplying the x value by a negative reflects it over the y-axis. So here, this point gets reflected over here. And this point gets reflected way over here. Okay, so it would look like that. So you can think of it as over here, the y values, the original y values, get multiplied by negative. And so then here they are. And over here, the original x values get multiplied by negative. So if you had a point at 1, it will now be at negative 1. If you had a point over here at 4, it will now be over here at negative 4. Okay? All right, and then let's take a look at vertical stretching and shrinking. And then after vertical stretching and shrinking, we'll take a look at horizontal stretching and shrinking. Okay, so if you have your parent function f of x, and then you multiply that parent function by a constant, then one of two things happens. Okay, so you either have a stretch, okay, and that happens if this constant c is greater than 1, then you have a stretch. And you can try to imagine if you're multiplying your original y values by a constant that's greater than 1, now all of those y values get bigger, right? If you multiply those, uh, original y values of the parent function by a number that's between 0 and 1, like 1/2 or 1/3 or 2/3, right? If you multiply by a number that's between 0 and 1, then all of those, think of 1/2. So if you have all these y values, these original y values of your parent function, right? And now you multiply them by 1/2. So now you're taking only half of their value. So now they all get smaller. Okay, so then shrink occurs. Okay, so here's a visual. Suppose that you have this. I'll do both cases. Okay, suppose that I have this graph. I have a point here, I have a point here, 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 and here. Okay. All right, suppose that I have this graph right here, this sort of snaky, wavy thing. Okay, so if I have this here and I multiply by a C value that's greater than 1, right? Then what happens is it gets stretched. So it's like these Y values, this one has a Y value that's not 0, and so does this one. It gets stretched. It gets multiplied by the C value. And so that now whatever that C value is, let's call that C, okay? And so then what happens, and this is now negative C, this goes down here, that goes up there, and we see this sort of vertical stretch, okay? If C is less than 1, greater than 0, okay, then that same graph, let's put it back over here. Okay. So if we multiply by like 1/2 or 1/3, all these Y values over here that are not 0 get cut. Okay, so then you have, oops, let me put this back. Okay, so you have this one here and this one here. And so now your graph looks like this, where you have this vertical shrink, okay? Where this was the original graph, and now you have this vertical shrink, okay? And we looked at this as, okay, well, to figure that out, I mean, when you look at the function being multiplied by the number, you should be able to recognize what's going to happen. When you actually do the graph, this is the one where we were saying, okay, multiply the original value, Y values, by that constant, okay? And then for the horizontal stretching, shrinking, so this happens when you multiply the x by a constant, okay? And here, if C is between 0 and 1, then that's when you have the stretch. A horizontal stretch occurs, okay? If your C value is greater than 1, then your horizontal shrink occurs. So again, kind of counterintuitive, just like the horizontal shifting. Okay, so let's take a look at that. So here, let's take a look when C is greater than 1. We'll look at the graph, and we'll take a look at a graph here when C is between 0 and 1. All right, so we'll use that same graph that we had over there previously. Okay, so point here, a point here. Okay, so let's just suppose that we have this. Okay. And we'll do it over here as well. That's your parent. Suppose this is your parent graph. Okay. Okay, so let's just suppose that we have some sort of a graph. Maybe it looks like this, okay? When c is greater than 1, then we have a shrink that occurs, a horizontal shrink. So when c is greater than 1, then what happens is these all get a little bit closer, okay? So these x values get multiplied, okay? Or divided here, multiplied by that fraction. So here, what happens is we get this this horizontal shrink. So it's like we have this wave occurring in less time. So we have maybe that there, that one goes there, and that one goes there. But these verticals stay the same. So if your highest point here is 1 and this is -1, then it will stay there. Okay, these won't change. Okay, your graph will still be between these two numbers over here. What changes is that this behavior happens in a more squished, you can think of horizontal space. Okay. So we have something like this. Okay. Whereas this one, if you have a C value that's between 0 and 1, then it gets stretched. Okay. So that maybe this one over here goes way out, and this goes way out, and this goes way out. Okay. And what happens is you have a graph that does, here, let me do something here. So there, and there, and there. So now what happens is you have a graph that does something more like this. So here again, your verticals, your vertical distance still stays the same, but now you have this behavior occurring over a larger horizontal space. Okay. All right. Let's take a look at an actual graph with an actual function. So let's take a look at this graphing. And let's go ahead and do this one. Graph f of x, which equals 3 minus 2 times x minus 1 squared. Okay, so this one might look a little odd here because you guys are used to seeing this 3 over here. So if that's the case, feel free to rewrite this as -2 times x minus 1 squared and then plus 3. Okay, so it's okay to move this 3 over here. All right, so let's take a look at what all of these numbers are doing to the parent function. So you should first recognize that the parent function is x squared. Okay, so the parent is x squared, which has the graph 0, 0, 1, 1, -1, 1, right? Okay. All right, so we know that this here is two things are going to be happening here with this -2. Number one, it's going to, the negative will reflect it over the x-axis. The 2 will give it a vertical stretch. Okay, so let's go ahead and write that down. The negative will reflect over the x-axis. The 2 will give it a vertical stretch. And the way we deal with this is just by multiplying the original y values of the parent function, okay? All right, and then this one over here, that's inside with the x, so this is going to shift it right 1 unit. And this one over here, this will shift it up 3 units. Okay, so let's go ahead and do the graph down here. We said it's going to go right 1 unit, up 3 units. Okay, so parent function 0, 0, 1, 1, negative 1, 1. This is my parent function. Okay, so I'm going to multiply the original y values by negative 2. And that will give me a point down here. I'll keep that one. And then I have that one. Okay, and this is how I get my reflection over the x-axis, and I get my vertical stretch, okay, because here this only had a distance of 1, but now it has a distance of 2, a vertical distance of 2, okay? And then I'm going to take those 3 points, and I'm going to shift them right 1, up 3. So this point over here goes right 1, up 3. Okay, so this one goes right 1, up 3, 1, 2, 3. You know what? I'll use a different color just to make it a little easier to spot. Okay, so right 1, up 3. So right here. This is going to go right 1, up 3. 1, 2, 3. And this is going to go right 1, up 3. So here is my parent function. I mean, my final function with these transformations done to the parent function. Okay. All right. One last thing. Let's talk about finding equations, and then we'll call it a day. Okay, finding equations. This is basically working backwards. So, for example, if you have to write the following, as an equation with the transformations applied. Okay, so suppose that I have the parent function f of x equals to absolute value of x. And I want to write a function that takes this parent function and has it shifted down to left 3. Down to left 3. Okay, so you would need to write a function that does this here, these actions over here, on this function over here. Okay, so if we want it shifted down 2, that means we have to subtract 2. And then if we want it to shift left 3, then we have to add 3 to the x. So let's call it a different name. Let's call it g. So left 3 goes with the x. Left is plus 3. And down 2 is minus 2. Okay, so this would be your final answer. Okay, so you're going backwards now. All right, go ahead and try this one. Suppose that this is your parent function and we want it shifted up 5 and right 4. Okay, go ahead and hit the pause button and then come right back. Okay, so then here, shifted up 5, so that's going to be add 5, and right 4, so that's going to be minus 4. So x minus 4, and then plus 5. All right, so that is it. If you have any questions, just email me or message me. I will see you next time.